Is that clear? So now, if at all we have an FSM state graph or a state machine, okay, so in the state machine we have some state graphs we will call the state graph, and we have some prescribed states, isn't it? So for example, if at all we consider some states like this, okay, I'm just example I'm taking, like we have some S2 that, okay, I'm talking about MVA, sorry, just for example. This is just an example. Please don't take that as a particular design or something like that. You can take like this, and then this one 1 by 0, and you can take it as 0 by 1, whatever it is. Okay, so all the states are filled. Now, this is a state graph given for you. Right. Now, this particular state graph has 4 states, isn't it? Now, once you decide the graph, you have some steps to be followed. Right. In the previous classes, we were designing very confidently Mealy and Morey only the state graphs. I have not told you how to proceed further. Okay, so how the circuit has to be created. It's very simple only, but we need to go through some steps. First and foremost step, once the state graph is ready, is reduce, or we can say reduction of states, isn't it? So now this reduction of states is not a new topic. It's already occurred in our previous sequential circuits, isn't it? What we have done there? There we have done any 2 states which are equivalent. Equivalent in the sense, if their next states and the outputs are similar, then we consider them as equivalent states, and we will strike out one of the states and replicate with the other, isn't it? So in that case, the number of what states will be getting reduced. Hence we will say the first step. And what is the benefit of that? What will be the benefit? If at all we have states getting reduced, the hardware implementation will be reduced. That means the number of flip-flops can be reduced, whatever. Right. So we can decide that the hardware implementation will be reduced once the state reduction is happening, isn't it? So first step is the state reduction. Right. Now, second thing. There was a doubt on the second thing. State assignment. Now, what is the state assignment? Now, if you go back and see the state graph, we kept is in very simple notation that we have some alphabets picturized or portrayed as states. But we don't know what exactly they stand for. In fact, if at all you see, once the state graph is ready, I really don't know how many variables, binary variables have to be assigned for that particular state. Now, just hold on. If at all you see this example, how many states are there? 1, 2, 3, 4. Okay, so there are 4 states. Now, can I assign 2 variables for this one? For this state graph, can I use 2 variables? That means the 2 variables undergo some changes. That means I can represent 4 states with this, isn't it? Or more than that also, PQR. Means 3 variables also you can do, or 4 variables you can do, but it's a waste of variables only, because there are only 4 states in this particular graph. Hence I confine that with 2 variables. Is there any doubt in that? Like how I am taking it? Now, if you can have 5 variables, I have no choice. I have to use 3 variables only. Do you agree for that?
Yes, ma'am.
Right. So that means the first idea is minimum variables are possible, please do with that. Otherwise, you have to go for a if at all I take 2 variables. Please add a third variable for this particular example. Please try to understand. Did you understand that? So now, first step in that is assignment of variables. PQ means these are variables. Right. Next. So I have to assign these variables to the carefully understand. So these variables It can undergo like this. That means you can take that as P bar Q bar or P bar Q like that. So in midterm combination also you can take. So I have 4 options readily available, right? Now, going map the states with this particular values. Please try to understand. I am trying to map that. One is the variable selections, number of variable selections. Second one is the assignment or the mapping of the states with the bits. Okay, now, so we have to here use a really different methods. Like see, I can arbitrarily choose S0 is this, S2 is this, S1 is this, and S3 is this. It is arbitrary because there is no rule. I can have an arbitrary or a random assignment for these states. Is that correct? Nobody can stop. No problem. So this way it is called a random assignment. Now, if at all we do a random assignment and proceed further, what will be the next step? The next step is nothing but I should design a flip-flop equation, isn't it? I should take a flip-flop relevant flip-flop which can finalize this one, and then afterwards I can design the sequential circuit, then the state equations, blah blah blah, isn't it?
Yes, ma'am.
I am not, yes, if at all I am not going to this random assignment, carefully understand, and I will take a particular procedure in assigning every bit or bitwise assignment to the states. Why? Because if you see your example in the previous classes, when we are designing the sequential equations or the sequential circuits, the present state and the next state are linked, isn't it? And afterwards you will use the state equations to reduce for using K-maps, isn't it? That means we go back to the corner maps and then try to understand in the K-map, if at all you use the boxes, a 1-bit variation, then it is fetching to reduce the complexity of the hardware, isn't it? Just see, number of variables is 2. I must use 2 flip-flops. That is correct. Nobody can change. But I can reduce the external combinational circuits. How? If at all I assign the states which are neighboring or which are adjacent. Like, just see. Now S0 is this and S0 next is going to S1. Right. So if I assign this particular one to S1, right, it is fetching. Why? Because they are adjacent. Just have a link between the movement of the states. Like from here to here it is moving. So better to assign them very closely so that my combinational circuits when I use the K-maps can be reduced. Right. Now what is another one? Now S1 to S2 is going here. So S1 to S2 will be beneficial if at all you go here. Then S2 to S3. So 1-bit away assignment so that I can rightly correlate or assign the neighboring states together. Then this is called not a random assignment. This is a flow. This is a neighboring assignment we will see. So as of now, you have only these two. You either go for a random assignment and then go for the procedure and then design the sequential circuit. Otherwise, you reduce the complexity of the hardware by choosing a better or a clever method of this neighboring assignment. Then afterwards, design the present state and the next state, then state equations, then afterwards the sequential circuit. So this will be the next step. Right. So this is the normal flow we will follow whenever we are designing a FS7, finite state machine. Is there any doubts?
Ma'am, can we say that
S3,
S3 is adjacent to S0, so 1-bit difference should be there?
See, now question comes like I have started from the starting state and moved towards the S3. So S3 and S0 cannot be adjacent. I went this way, na? So S2 and S3, till that level I can establish the assignment, like neighboring assignment. But S3 and S0 is far ahead. I cannot do that. If I am going for S3 and S0 assignment, so you will have a different assignment level. Definitely. So neighboring state assignment, this is one of the neighboring state assignment. I am not saying this is the perfect one. This is not a perfect one.
Ma'am,
Possibilities, isn't it? To map them. So this is also like that. I remember somebody asked, like, can we do any arbitrary assignments or something like that? But not possibility. Arbitrary assignments does always the complexity increases. But if at all you choose in this manner, you can reduce the complexity. So as I don't know who prompted it, S0 and S3, if at all you think they are adjacent, so your assignment should be completely different. So you may give S0 0 0 starting, then S3 as 0 1, then afterwards S2 as something else and S1 as something else. No problem. That time S0 and S1 are far away, isn't it? Is it correct?
yes, ma'am. One more thing is there.
Yeah.
You told that S1 is adjacent to S0, so there should, if there is one bit change, then our circuit will be easier.
Yeah, our
Similarly for
circuit means, wait, I have to make a correction. Our circuit means the combinational circuit, the gate logic is there other than the flip-flop. That means in the state equations, whatever we do, there we can have a less complexity. Okay, now go ahead.
so similarly for S1 and S2, there so there should be one bit change between
Yeah,
S1 and S2.
yes, but 2-bit change is there. So betterness is S3 is better here. S3 is better here, 1-bit change. Or which is better?
Yes, ma'am.
Which is better here? What assignment I can go for that? Which state will be better? For S1, which can be adjacent? Anything? See,
S1 to S2 as well as S3. So
S1 and S3, if at all you take, that will be better because this is 1-bit change. Then afterwards, this can be S2. Yeah, sorry. This can be S2. Yeah, it's good. It is good assignment. Because 1-bit change, we are trying to map their neighboring state assignment. Is that okay?
but ma'am, S1 is going to both S2 and S3, so we can do any one of them, I think.
Yeah, exactly. See, this is what? This is the chances only. We are trying to, this neighboring assignment is just an arbitrary concept. Not with a particular cleverness is required, but random thing not required. Okay, that's what I told. Go for a assignment in such a manner so that the complexity will be reduced. So that is the best possibility. That's all. Other than that, nothing. There are no rules in that. In fact, there are no rules in that. Why? Because ultimate target is after this, the present and the next state will go for my hardware implementation. Hardware implementation means then you can see how many gates are involved in the process. That actually matters a lot, isn't it? All the time we are after the reduction, isn't it? All the time we are after the reduction of the reduction of the hardware, isn't it? So hardware reduction only can be led if at all a intelligent way approach is taken here. Why? Because in the starting of the design, I cannot change my sequence detector. That is fixed. Second thing is some level of reduction can be possible if there are equivalent states. Third thing is a better choice of variables. Fourth choice is neighboring state assignments. Then all together they can hit for your efficient hardware design. Isn't it? You'll agree for that?
Yes, ma'am.
So this is how the procedure will be. Right? Whether it's Mealy or Moore, doesn't matter. But these are common. These are fixed. Right. Now you tell me, if at all I increase one more variable to design this one. So is that a what? Useful way to do that? Three variables representing these 4 states. So I have unused states so much and 3 variables I'm compromising and 3 flip-flops I should start with, isn't it? 3 flip-flops I should start with. 3 variables in that so many unused states are there. So all these are. So I think I will waste hardware here, isn't it? It's not a good way. Yes or not?
Yes, ma'am.
So this is how we have to choose depending upon this. If I have one more extra state here, I am not what? I may not or cannot use 2 variables. I have to go for the third variable because one more extra state. That means 5 states totally. So 5 states totally, I require 3 variables to represent. So in that case, I have to use 3 variables. 7 states can be possible. Unfortunately, I have only 5 states used there. So some of the assignments are out, but we can have a plus point there. So we can choose a neighbor state assignment nicely among the unused states also, and we may do better. We don't know. That is again the choice factor there, isn't it? So we can go for all the possibilities of the neighboring assignment and do the best assignment so that the complexity can be reduced to the minimum possibility, isn't it? That's how the complexity is reduced, because the number of flip-flops cannot be changed, but the rest of the combinational circuit, the AND gates, OR gates, everything which will aid the original sequential circuit design, that can be reduced because they matter a lot. They are the one who are counted in the hardware complexity. Is that fine? Yes or not?
Yes, ma'am. Yes, ma'am.
Right. So
Yes.
now, after this, what happened is the next step, very close to the hardware implementation. See, I can have FSM, I have a state graph, and I can easily go for the circuit design. But there is one more way, which is very similar for a designer, or very easy for a designer to go into the hardware directly. Right. So you can, after listening to that, you can say that why ASM charts are required. They are called ASM charts. Now, how I should explain you this ASM? Arithmetic sequential machines, you can say, or algorithm sequential machines, you can say. There are 2 ways to. Okay, we can say algorithm state machines, algorithm sequence machines, arithmetic sequence machines. All are the same names. ASM is finite state machine, but after that, this is mostly they will say it as algorithm. Algorithm, A stands for algorithm. Then afterwards, AS for sequence machine or state machine. Okay, right? So now ASM is a chart, or I can say it's a pictorial representation. Now, if you see, pictorial means it's very interesting, isn't it? Pictorial means interesting way to explain a thing. This is always there in the design also. So if at all, I have 2 options, like you are reading a paper, consider, you have a pseudocode explained. You know what is a pseudocode? Algorithm in steps. If at all a procedure is explained in steps and a procedure is explained in a flow chart, which will be preferable or which is very quick to understand? Honest answer. Huh?
Flow chart.
Flow chart. That's right. So that's where the flow designers has checked out or benefited more when they check out this algorithm chart rather than a FSM chart. I mean, this one is also there, graph is also there, but we can also have a flow chart. Now, how to prepare a flow chart, right? I don't want to discuss on this state machine right now, but in a flow chart, what exactly is the flow we follow? What is the flow we follow? You have any idea? You might have done in the first year. What you have done? C programming or something you have done? You have a start, then afterwards you have some square boxes, rectangular boxes, then you have a decision nodes, you have paths, yes or no, then afterwards ultimate decisions, then afterwards you will have a feedbacks, isn't it? Did you see that? Do you get oval shapes in that? Just to say it is start or stop. You will have some rhombus like this, a decision tree. And this is a rectangular box where you will explain the step. You remember this? No.
It is not there.
It's not there. Okay. Flow chart you told. So I presume that you people already know what is a flow chart look like. Flow chart is nothing but you have some trees in that, like you have some branches which will explain the flow where to start. Start means we always use an oval type symbol. There is a symbolic arrangement. We say oval is there, then we have a rectangle boxes where you encrypt or you use the equations inside that. Then afterwards you will have a decision making like this especially, and you will have 2 paths, yes and no path, isn't it? Yeah, don't tell me, in your schools also you might have used. So is F greater than R or something like that. This is just an example I'm telling. So S means do something, no means do something, isn't it? Then after doing that, then you will finally you will stop. Or repeat the procedure, you will go and show something like this. Isn't it? This is how a flowchart is made. Yes or not? So similarly, the FSM chart or the FSM machine can be designed as a flowchart also. And it is very easy to understand because each FSM chart, like for FSM machine or FSM graph, you have different states. And I'll pick up every state and explain pictorially and say how the path enters, like how the flow moves. Okay, now hold on. So I will try to show what are the symbols normally used and I'll explain you also. Right, just a second. I have only one particular figure to show. Oh. Yeah, this is I picked up from this one. Just a second. Yes. Yes. Just a second. You are able to see any, this?
Yes, ma'am.
Yes, light. Okay. Now, it's a little complex there. I'll make it very simple. So, first and foremost, you have a one symbol called a rectangle symbol. You don't take it as square, it is a rectangle symbol. Okay. So, now the rectangle symbol which is used there shows the state. Okay. Shows the state. Now, what do you mean by state? State variable is means the state, like in the circle we use, no? In the media or Moore, whatever it is, we use like this. So this particular stuff is entered here. Okay, and are you able to understand? Like for example, this is a state. State, it is so many states are there. One of that is S0. So I will try to write S0. So this particular graph or this particular rectangular box consists of the state name. Okay, it consists of the state name, right? And if it is Mealy type, what happens? The output will be not there. So I will just leave it like that. Right? Why? Because the output is in the path. Na? If you remember Mealy and Moore, what is the difference between that? In the Mealy, the output will be shown on the path, whereas in the Moore, it will show inside the state itself. Isn't it? Yes or not?
Yes, ma'am.
Yes, ma'am.
Yes.
So,
Yes, ma'am.
Yes, ma'am.
hold on. So what happens? So this rectangular box state is already there. If it is Mealy type, I cannot show. But if it is Moore type, I can show here. So here I can say this is output. Okay. So output means whether if it is there, you write Moore type. If it is not there, don't write. Just show a slash. That is what explained there. Okay. And one more thing. This is not hanging in the air. It has a path. This is called the entry path. Right? Now hold on. Entry path will not be multiple. It will be always having only one. Yes? So multiple paths won't be there. I cannot have like this. If you remember, just see, can I have multiple paths? From every state, I can have only two paths going on. Entry path is only one. Yes or no? You will agree for that? What?
Yes, ma'am.
So that's all. So entry path is one which is shown here. We will call that as entry path or data path. Entry path or data path. Okay. So this is how we will show the state name. Right. Now you can ask me if I have another state called S1 somewhere. So that will be shown in another box. Right. And I'll establish the link between that state and this state in the later. Okay, so hold on. So we will not rush into that. We will go step by step. Okay, now after this, what is the next problem? What is the next thing? So this state, particular state is moving somewhere. I'm talking about a Mealy one. Okay, so if at all it is moving, it is taking some input and giving some output and going to some state, isn't it? Now, how to show here pictorially? So, what I will do, I will try to take a decision. What is that? I have an input and my input has two parts, right? Either 1 or 0. So, now this particular stuff is what is shown there. Check out in the slide. You have a decision making and that line is there now hanging on the decision node is coming out from a rectangle box which we will call this as a state box. State box. This is called decision box. What is decision box? Who is taking the decision? The input is taking the decision and you can tell me why you have used the symbol X. X is normally used for the input. That's why I have used. And you can question me if I have two inputs, then your graph will be a little complex. So we will go step by step. I have only one input because I have only one input and one output. At present, I will keep it very simple. Then I will go for two input and two outputs, all those things. Okay, go for, with baby steps. Right? So the X is there and it has two decisions to be taken. If 1 comes and 0 comes. Is it the same symbol shown in the graph? I mean the slide? A decision making? Yes or
Yes,
no?
ma'am.
Yes. So this is how it is. Now decision making 1 and 0. Then what you can put like this. Otherwise, it's best way and a beautiful way to show is like this. Right. So once if it happens like this, then if x is 1, sorry, x is 1, it moves this part. If x is 0, it goes to this part. Right. And also we will try to explain what output it is. Hold on. So you don't get confused. This is the input and it is going to another state which I have not shown yet, but intermediate I have shown what output it is taking there. Please try to understand. Now, I'll show you a complete example also, don't worry. So what is happening? X decision is going to another state. So I don't know. After this we will decide with an output this. So this is might be 1 or this might be 0. We don't know in a graph. Right? So the X decision is going to an output. This X decision is also going to the output. And after this, maybe you are going into another state. State 2. We don't know. Right? That depends upon the graph. Right? Otherwise, after this, you might go to a restart state also. Means back. We don't know. So the first and foremost thing is this particular stuff of explaining each state is nothing but a sequential link, how the state is behaving with the input and giving an output and flowing towards the next state. This is what is shown in a ASM chart. Right? And you can have only 3 symbols. If you see, all the 3 symbols are provided there and I am giving the same thing. One is the state box, another one is a decision box, another one is called a output box. And otherwise, I don't know what is the name they have used. Yeah, conditional outputs, whatever it is. So we can say output box. Is that clear? Is that clear?
Yes.
This,
Yes.
ma'am, this conditional is only for millimos.
This conditional is only for Millet. Why? Conditional is there for Moore also, no?
In the slide,
Output only won't be there. For Moore, outputs won't be there. Maybe from here directly you will enter into the state for Moore. Is that correct?
yes, ma'am.
Yeah.
Yes, ma'am. That's what I am.
Understood. No problem. So is this clear? So we have to link, map every state and its history onto a flow chart. Right? You can ask me, it's a tedious work, but afterwards, once we design these charts, it will be very useful for the hardware design. We can say in designer language, it is one step away from the hardware design. Whereas FSM, say 2 steps away from the hardware design. Graphs are not meant to be used for design. A designer only understands this pictorial diagram, right? Hence, we should know as a digital designers, we should understand like how this flow will work out, right? I can give a small example. We will do one small example. It will be easy for us. Okay, with this three boxes only. All the time, this three what symbols, nothing much. Okay, so now let us take an example already provided to us a graph. It has 3 states. Okay, so as 3 states are there, sorry, 3 states are there. It is a relay type S1 and this is S2. It's better I will use small letters. It's easy. Otherwise, this will be chart will be S2 and this is S3. Okay, so this is S0 is a start state. Let me get that. So this is just a second. It is S0 provided to is already 0 by 0, right? And it is going to S1 1 by 0. The purpose of this particular graph is to have 101 detection, it seems. So already we have done that. Consider that we have already done it. So we have already done some at this one. And right. This is how it is given. Okay, yes, not S1, S2, S3. And also the state assignment is like this.
Ma'am,
Yeah. What happened?
S1 is not drawn here.
Okay, so S1 and S2 is 1. This is assignment already provided. Okay, now we have to show the ASM chart for this. Right, now state assignment is given, state diagram is given, state graph is given, we have to draw the diagram. Okay, so now let's start with the starting state. So this is our starting state. Okay, the shaded one is the starting state. So how I am going to show? I will show it as a state space box. All the time. This is my box. So what does this box consist of? I will have only the state name. So state name is S0. I cannot have any output because it is a relay type. So it is shown with a slash and a vacant space. Right? Now, what is this happening? This is trying to take a decision with a single input X only, because on the input side there is only one bit happening. So I will presume that it is only one bit value. So one bit is having 2 rows, 2 ways to go. What is that? One is a path which will take to 0 and another path which will take me to 1. Is that correct? Or 1 or 0, 0 or 1, whatever it is. So normally this is the notation. Which side ever you want to take, this side, normally 0 this side and 1 that side they will show. Is that okay? Right. And now what is the decision next? What is X is equal to 0? What it is doing? A conditional output. It is like a oval. Output is that which is 0. Right. So 1 also is 0. 2 conditional outputs. Is that fine? And then when X is equal to 0, a conditional output of 0 has come and it has been traveled back to this. The arrow I can show. Is that fine? A conditional one, this particular one has traveled back. Is that explaining that? A 0, it is having an output 0 and it is taken back here. Is this the same thing what is shown? And here you can say this is the state assignment 0. Okay. And then as that is equal to 0 from here, what I can show? It is going to 1, it is going to another state called S1. So from here, I will have a new box S1 with no output. So I can say This is a complete state history. Of this particular state. And see, 0, 0, why I kept there? Here to show that its assignment is 0, 0. Is that clear? Because this is one state completed. One state, what it is doing is pictorially shown. Any doubts in that? Yes or no? Is that
No,
easy?
ma'am.
Yeah, right. So now afterwards the journey started to S1 because this is already done this side. So S1, what S1 is doing? So S1 is having what? Another decision making. I don't have any output, so I will have a decision maker X. Who is the X doing? X has again two parts. Then it's 1 and it's 0. So you can have a beautiful drawing with nicely with scale, pencil, eraser, everything you can use. So what is happening? Conditionally 0 time. X is equal to 0. Please stand. It is going to S2, but with a
0, output 0.
yes. Right, afterwards I will tell. 1 it is S1 is staying back at S1, right, with an output
0.
S1 is staying back and back to 1, so that I will show, but with a conditional 0. So I will have here also Z equal to 0. Then what I should do? Z equal to 0. I should take back now. So this is a back part. Back to this. Right? So now S1 assignment is what? What we have taken? 0, 1. So 0, 1. Right? And from here, the path went to what? S1 went to S2, isn't it? So you can little bit check out and put a rectangular box, right? And with no output, and then I can say that this second box, this particular stuff, is my second one. So first box is over, second box is over. Second box explain all about S1. Right? Now S2, what S2 is doing? S2 has come anyway from this, then what S2 is doing? S2 is also having two decision maker. Isn't it? S2 is having again 1 and 0. Yes or no? So there is 1, there is 0. Right? And here we have some Z. What is this? Z supposed to be? X is equal to 1. Z is equal to 1. It's fine. But where it is going?
It's going to S1.
Yeah. So how I will show?
S1.
So best way is to take this one, or you can take here from here and then nicely combine at this part. You can show this way. Right? So this one. You can show that it is going to S1 because already feedback is applied. Isn't it? So what is that equal to X equal to 0 doing? X equal to 0, it is Z equal to 0. So what it does? It is taking a path, conditional path, and you can join here, I guess. Isn't it? With this path. And you can say this one. There is a, sorry, you should be able to nicely portray that in this box. All about beautification. So S2, what it is assignment is? Assignment is 1. So that's how the 3 boxes without overlapping, we have told about them what they are doing with their assignments also. State assignments also provided. If you can readjust them so that you will not have a crisscross, nicely how the graphs are redirected with the arrow marks, and then you can check out. And if you see, we are following all the regularities. What is that? We don't have multiple outlets. Right? So conditional ones, how they are taking, the decision box, how they are taking, all are clearly shown, isn't it? Is that correct or not? Easy?
Yes.
This is just the pictorial way to show. Now, yes, Any doubt? Somebody is asking doubts. Yeah, you can ask. No problem. Yes, no doubts? Hello? You guys are there? Still processing?
Yes, ma'am.
Yeah.
We are there.
Yes,
No
ma'am.
doubt.
You are there, very good. But
No
are you able to understand? See, this is very simple to design. Only thing is, we have a little technical stuff to show. We have rectangular box, states box, we are telling, we have oval shapes, we have decision makings, and then the movements neatly done. Okay, now do you find any crisscross over here? Or the flow sequence? The states are there and their sequences are clearly shown. And you can see the timing sequences are also clearly given. Why I use the word timing sequence? Because one after another, like you see, S0 afterwards, S1 only is preferable. Why? Because after this it is going back to S0 only. Na? S2 is not there in the picture. So the sequence is something like S0, S1, then S2 I guess. Right. So the flow sequence as well as the timing sequence is clearly mentioned, isn't it?
Yes, ma'am.
Yeah, that's how it is. ASM chart is being considered. Okay, so the ASM chart is somehow is a simple replicate of your FSMB. Right. Now we will increase the complexity. Right. Now what can be the complexity we can think of here? We can think of, let's go step by step. If at all we have two variables, two input variables that decides, like x1, x2 are there, then afterwards decision is making. So what changes we can incorporate here? See, here we have only one input variable and we are taking a decision from a state space. Right? Now if I have two variables, x1 and x2. X1 means it is going somewhere and x2 means it is going to another state. And in x1 also I have 1 and 0 and x2 also 1 and 0. That possibility is there. So how I am going to show? How I am going to show? See, I have a state space now. State box. Right. After this, I have to come for this one. Right. I cannot incorporate 2 here. So what I am going to do? Yeah, I am asking you inputs. So what can be the best possibility? So can I
Making
have,
it
yes, ma'am. Can I have two multiple outputs?
making a different type of decision box.
Making a different type of decision box means like what? Like you can show it, you can draw it and show. You can use a marker also.
Ma'am, we
Yeah.
use,
Go ahead.
we can use three decision box X, Y.
Three decision boxes. How? Like what? Like how you wanted it. Yeah, somebody is telling. So, like if at all you can show pictorially, it's better. Anybody can draw and then show. Like you can post it.
Ma'am, for 2-bit output, na input.
No, 2-bit input. Afterwards, I'll discuss about output also. I think output has no problem. Output has no problem, I guess. But input, how I will show? That's what I was asking. In the decision box, I can fit only one variable. Or is there any variable that I can fit two variables inside a decision box? Yes, Aditi?
Ma'am, under Ma'am, under x1 0 and x1 0, we can implement x2, then again 0 1,
Okay,
and
just
for x1,
hold on, Sulagna, wait. What you are saying that under the state box, first one I will put x1.
yes, ma'am.
Okay, I kept x1, okay, fine. Right, then
From 0, then again we'll implement x2, then 0 1, and for 1 again x2 0 1.
so this one and then one. So from here again another decision box you are telling.
Yes, ma'am.
Okay, so that decision box, this is also x2, this is also x2.
Yes, ma'am.
Okay, hold on. So it will check what's the meaning of that. I'm trying to interpret. So x1, if it is 0, it is going and checking x2 and then again taking decision here like this. And x1, if it is 1, again it will go and check x2 and again taking decision here. Is that what you are wanting to tell?
Yes, ma'am.
Okay. So any contradictions here? Any contradictions? The whole class is there listening to Suragna.
It's correct only, ma'am.
So possibilities are there. So somebody has posted something. Oh, Hassan has done. Okay, let's see what Hassan has posted for us. Okay, so that's what he was telling. So she was also telling the same thing. Yeah, x1 and x2. Okay. So now x1 and x2. That means all the possible combinations of the inputs you have vibrantly worked out, isn't it? So you went step by step. So x1 you finished off. Again you checked for end statement of x2, all the possibilities. So it is worked out. Fine. I don't think we have missed anything here. The same thing if you go for 3 inputs, what maximum will have? x1, then x2, then x3. In all levels we have to compete, isn't it? So first we will check x1, then afterward the possibility of x2, then x3. So how many combinations you will get? Decision boxes. What happened, girls? Class and girls, what happened? How many possibilities will come? x1, x2, x3 are there. 3 node decisions. 3 inputs.
8.
8 combinations. Yeah. So we have to go step by step. Right. Okay. Hold on. So this job is done. Now, second point. If I have 2 outputs like Z1 and Z2. Okay. So my state box has S0 with Z1, Z2. And I have only one input, X. So I have like this 0 and this is 1. Okay. So I can easily show Z1, Z2. Isn't it? Here also, what is Z1, Z2 we can show. Can I do that? Because one input and 2 outputs, 2 conditional outputs. So Z1, Z2 equal to 0, 0 or something you can write, no problem. So you can pictorially show Z1, Z2 equal to 1, 1 or 1, 0 we can show. We can show with a single input, right? So with 2 inputs, again the same scenario comes. So x1, then x2, x2, 0, 1, 0, 1 and their conditional outputs will come. So the branch expands. Is that fine? Yes or not?
Yes, ma'am.
Right. So this, yes. Now this is the ASM chart, which and that is the complexities what we have designed for. Hold on. So this is the ASM chart of a Mealy machine to show or to detect the sequence 101 with the state assignments like this. Okay. Now I want you to design the same 101 sequence detection with the Moore type. Sorry, Moore type or a Moore type. Okay, with the what? Not with a random assignment. You go for a neighboring state assignment, the possible neighboring state assignment with Moore. 101 detection only. It's FSM, it's ASM, and the state assignment. State assignment is up to you. Is that okay? Please take down. Design a Moore machine that detects 101 sequence, right? and what else? 1016.
Ma'am, you are not audible.